talking about several angle and side inequalities in triangles. And so let's begin with the simplest sort of entry into this, which is the idea of the isosceles triangle. If we check out this picture of triangle CDB, not CAB, but CDB, then that one looks isosceles. What we know about isosceles triangles is that if they have equal sides, then they have equal angles. And if they have equal angles, then they have equal sides. So to be more precise, if angle CDB equals angle DBC, then the side CD is also equal to the side CB. So if two angles are equal in a triangle, then the opposite sides to those angles are equal. If two sides are equal, then the opposite angles to those are equal. So that's all about equality. What happens when inequality appears? What happens if we have a triangle ABC and the sides are not equal? Then we expect the angles are not equal, right? And of course, we can conclude that the angles are not equal because we know that the thing is not isosceles. But what is the relationship between the sides? Does it correspond to the relationship between the angles? Notice in this picture of the triangle ABC, angle A is smaller than angle B, and the side opposite angle A is shorter than the side opposite angle B. Will that always happen? Let's prove that it will. So let's take an arbitrary triangle ABC in which the side B, that is AC, is greater than the side A. And what we'll prove is that the angle opposite the side B is also going to be greater than the angle opposite the side A. So in other words, the relationship between the opposite angles is the same as the relationship between the sides. So here, side B is longer. So what can we do with this? If this side is longer, then we can identify a point D, which is equidistant from C as B is. In other words, we can produce a little isosceles triangle within. And it must be contained within because side B is longer than side A. So CD is equal to the side length A here. So having achieved this little this isosceles triangle here, we can say for sure that this angle CBD is equal to this angle CDB. Is that helpful? Well, maybe not. So let's see if that's helpful. So we have the equality of these two base angles of our isosceles triangle, but can we relate that to the original base angles at A and at B of the original triangle, the angles in particular CAB and ABC? So notice that, you know, we have the equality of these angles, but these neither of the base angles in the original triangle is equal to these. But they are related to them, and by using these two angles and their equality and relating them to the original angles A and B, then we can deduce that B is bigger than A. How does that work? Well, first let me argue that angle A is smaller than this angle CDB. Why is that? Angle A plus angle ABD plus angle ADB sums to 180 because those three make a triangle, namely the triangle ADB. But also this angle here is supplementary to this angle, CDB, and so ADB plus CDB sums to 180. If these three angles sum to 180, but also these two angles sum to 180, then this angle A must be smaller than this angle. And that tells us that angle A is smaller than the base angle of the isosceles triangle, namely CDB. What about angle B? Well, angle B contains this base angle of this isosceles triangle. Angle B, that is ABC, contains the angle DBC. So clearly, angle B is bigger than the base angle of the isosceles triangle. So A compares smaller to the base angles of this isosceles triangle, and B compares larger to the base angles of the same thing. And that means that A must be smaller than B. So what we've proven is that if the sides have an inequality, side A is less than side B, then indeed the opposite angles, angle A and angle B, have the same inequality. Angle A is less than angle B. Okay, so that's an if-then, that's a one-directional statement. Let's talk about what happens if we try to look at the converse. What happens in the other direction? What if we know that we have an inequality of the angles? For example, what if we know that angle A is less than angle B? Then can we deduce from that that side A is less than side B? Well, actually, this follows from everything else we know already. If the angles are unequal, then the triangle ABC can't be isosceles because it has unequal angles. So one of these sides is bigger. And if it were this one that's bigger, then by what we just now proved, then the opposite angle to it would be bigger. So, so this one can't be bigger, so it must be smaller. So that demonstrates that if a side is greater than another side, then the opposite angle, sorry, I just figured wrong. If this side is greater than an opposite side, then the opposite angle is greater than the opposite angle. And conversely, if an angle is greater than another angle, then the opposite side to it is greater than the opposite side to that. So you can read about this here. I encourage you to pause, and you can see how this is written up formally here. It follows from this that if we have a triangle and it has an obtuse angle that is greater than 90 degrees, then the side opposite that obtuse angle has to be the largest side of the triangle, because an obtuse angle is greater than any other angle in a triangle. A triangle cannot have two different angles both greater than 90 because it has to sum to 180. So if you have an obtuse angle, then that angle is greater than any other angle in the triangle. So the side opposite to that has to be the longest side of the triangle. All right, what's next? Next, we're going to use what we know here about angles and sides and their relationship, and we're going to prove something that is so perfectly obvious you would think that doesn't need proving, but it actually does. We're going to prove that the function sine is an increasing function. So that's this theorem. On the range 0 to 90, the sine function is an increasing function. Now it's not increasing on its whole domain, of course, because it's sinusoidal. But on the range 0 to 90, sine is an increasing function. And this diagram is going to help us prove that. You can feel free to read the text, or I'll link to the text in the comments. So what we're going to do here is, so what does it mean to say that this is an increasing function? It means if we have two different angles in this range, alpha and beta, and alpha is less than beta, then the sine of alpha will also be less than the sine of beta. So that's what it means for this to be an increasing function. Basically, bigger angles have bigger sines, at least within this range 0 to 90. So let's see how this works. Let's suppose we have two angles, alpha and beta. Now, what we're going to do is we're going to choose a unit circle. So this will be our unit circle. And then we're going to choose points B, C, and D so that we're representing both angle alpha and angle beta. Now, it's not marked in this diagram, but angle alpha will be the angle BAC. And angle beta, which I've represented slightly greater, will be the angle BAD here. So that's beta, the larger angle, compared to the smaller angle. And I've made it just a little bit larger so that it makes it a little bit hard to tell. Now, the sine of that angle can be represented in this picture. So if this is indeed a unit circle, then this radius is 1. And the sine of the angle alpha is going to be the opposite over the hypotenuse in a right triangle. So all we have to do is construct a right triangle. So let's do that. We'll drop a perpendicular BE to the segment AC. And since we're also going to do the same thing for beta, we'll also drop another perpendicular BF to the segment AD. Notice that since AD is at a different angle, this perpendicular falls at a different angle here. So we've dropped two perpendiculars, BF and BE. The length of BE is sine alpha, because this thing divided by 1 is equal to the sine of this angle. The length of BF, for the same reason, is sine beta. So all we really need to show here is that BE is shorter than BF. How are we going to show that? Well, notice the angle at E. The angle at E is a right angle because we dropped the perpendicular. That is, BEA is a right angle. Plus, well, a little bit more, because the segment AD is below the segment AC, and so F lies down here, and so we get a little bit more. Now, I don't know what this angle AEF actually is, but it's a little bit more, right? So if we look at angle BEF, that angle BEF there is a 90 degrees plus a smidge more. And that means that that angle is obtuse. So who cares it's obtuse? Well, if that's an obtuse angle, then when we look at triangle BEF, its longest edge must be the edge BF. But BF is sine of beta, BE is sine of alpha, and that shows that sine of beta is bigger than sine of alpha, because that's the longest edge of that triangle. So here, the isosceles triangle inequality stuff leads us to an understanding of the function sine and leads us to a demonstration that sine is an increasing function. So you can read that form, you can pause the video and read that formally written out here. Now, what can we do with this? Well, now we're going to reason next about what happens if we have two different angles inscribed in a circle. So this is a sort of a technical lemma that we'll use for the Steiner-Lamius theorem soon. But the angle is, the theorem is, if you have two different inscribed angles, and they're not both represented in this picture here, I've only inscribed one. If you have two different inscribed angles and one of them is bigger, then the bigger one subtends a bigger chord. So in other words, if I have another inscribed angle and it has a bigger angle measure than D, then it will subtend a bigger chord. So AB, so in other words, if angle D grows, chord AB will grow larger. Now, this is, we need to be cautious here. This is for angles less than 90. That is for acute angles. So in other words, if we have two acute inscribed angles, then the larger angle gets the larger chord here is basically what we're saying. And this follows from the fact that sine is increasing. So let's look, plus our inscribed angle theorem. So if we have angle D here, it subtends some chord AB. Well, we know that there's a relationship between the central angle and the inscribed angle here. The central angle C, subtending the same chord, is exactly twice as big as this angle D, which means if you then bisect it by dropping a perpendicular from C to E, perpendicular to AB, so if you bisect this angle, and we get two right triangles here, then this portion, ACE, and this portion, ECB, are equal, and they're both equal to D because the central angle is double the inscribed angle. So angle D is again represented here and here. Well, the radius of this circle can be chosen to be, well, so the radius of this circle is R. That means that the length AE is exactly R sine D, R sine angle D. So AE is exactly equal to the radius of the circle R times the sine of this angle D, because the angle D is appearing right here inside this right triangle. And EB is also equal to R sine angle D. And that means that the length of the chord AB is exactly twice the radius of the circle times the sine of the angle alpha. So if you have one, so no matter what angle you have, the length of the chord that it subtends, if it's inscribed in a circle, the length of the chord that it subtends is 2R sine alpha. So if you have an angle alpha and another angle beta, then for alpha, the length of the chord is 2R sine alpha. For beta, the length of the chord is 2R sine beta. And if sine is an increasing function, then 2R sine beta is the bigger length. And that demonstrates that a larger acute angle inscribed in a circle will subtend a larger chord on that same circle. So these are our various length inequalities and length and angle inequality relationships that we needed to prove. And these will be used in order for us to give a simpler proof of the Steiner-Lemmas theorem.